Hello and welcome to this webinar on aluminum foundry alloys for different processes and applications. My name is Martin Hartlieb, and if you have any questions, you can find my email address at the end of this presentation. I hope you had a chance to look at our previous webinars. One was an introduction to aluminum foundry alloys and metallurgy in general, where we discussed alloy foundry alloys, alloying elements, different impurities in different alloys, achievable properties, and the typical applications of the different foundry alloy families. And the other one, very important, of course, casting technologies or casting processes, where we showed the different processes and how they really work, what are their advantages and disadvantages, and what are the typical applications for each of them. So just as a quick recap on the foundry process selection, you might want to first have a look at what is going to be the volume of the castings that I'm planning on making, and volume can be per month, per year, or in total. So if you have a huge volume, well, then you might want to consider die casting because you will have a big investment. This can be hundreds of thousands of dollars in casting and trimming dies, but then your piece price will be very low. The opposite, of course, sand casting, where you have a fraction of the investment just to make into patterns, but then your casting costs per piece will be much higher. So this process would be much more suitable for, let's say, making prototypes or small volume production, and die casting is only suitable for making very high volume production. Another criteria might be wall thickness requirements. If you want to go very, very thin walled, well, then die casting again can be very attractive. And if you want to go very thin, high vacuum die casting or maybe even Rio casting, this can make parts that have wall thicknesses down to below 1 millimeter. So very, very thin. Impossible to make, let's say, in a permanent mold or even in sand casting. The next thing would be tolerance requirements. So again, let's say if you are in die casting and you're even within one die half, you will get extremely good tolerances versus, let's say, sand casting, where you typically will get larger tolerances in also thicker walls. Surface quality, if you want excellent surface finish, then whether it's plaster cast, investment cast, or of course die cast, especially high vacuum die cast would be your choice. And then mechanical properties, and not just static, but also dynamic, fatigue, creep, impact, all of these properties are determined by the microstructure, by the alloy, and therefore the process and how you freeze the metal will have a big impact. Also how you fill the die. So in conventional die casting, for example, your properties won't be that good because you have a very turbulent filling. You often deal with porosity, especially when the walls get thicker. So in this case, it might be more suitable to go into permanent mold or low pressure permanent mold casting. Now, it's also the other way around. So the process will determine which alloy you should be using. For example, die casting, because of the high speed you're injecting the very hot metal, you will actually experience a phenomenon that's called die soldering. So if you inject a very low iron alloy that has not been corrected with higher manganese, you might experience a lot of sticking of the aluminum into the die. That's called die soldering. So die cast alloys are therefore usually high iron or have higher manganese. Some add even strontium to it, and that will limit your alloy choice. Now, if you're coming the other way around, you already have an alloy in mind, then a certain process might be the most suitable one. So if you have, let's say, a 206 alloy, very high strength, but also hard to cast, then it might be much easier to do this in sand casting versus in a permanent mold casting. So what are we going to cover in this webinar? Well, first of all, we're going to talk about these special high pressure die casting alloys, simply because high pressure die casting is the biggest consumer of aluminum foundry alloys, especially in North America. Then we talk about alloys for structural die casting, that's high vacuum die castings, because that is the fastest growing foundry alloy market right now. And then we look at the alloys for all other casting processes, so slower solidification processes, because they have a lot of things in common versus the die casting alloys. Then we have a look at alloys for high temperature applications, because we know that aluminum is not really very good when it gets hot. It gets very soft very quickly, and there are ways to improve high temperature strength properties. Talking about high strength, we have to look at which kind of alloys are suitable for really high strength applications that we need very often in aerospace or military applications. And then a few special requirements like anodizing or brazing. There are alloys that are capable of giving us very nice surface finishes even when they're anodized, or that can be brazed. Aluminum foundry alloys, we distinguish between rod alloys and casting alloys, and the casting alloys, well, they are kind of a compromise because the alloy must be castable to near net shape, so it has to have very good fluidity to fill the mold in its liquid status, and then feeding behavior during solidification. It needs resistance to hot tearing and hot cracking during the solidification. And the mechanical properties are really achieved through the chemistry itself, the heat treatment, and careful part and gating design, so solidification control and local solidification rate. So that will determine the microstructure. And last but not least, control of the defect structures, because very few castings are completely porosity free, although sometimes you see this on a drawing that specifies that the casting has to be porosity free. So unfortunately, that is normally not possible. So let's have a look at a few different foundry alloys, and we can see here the different families. So a 200 series alloy, A356, very castable, 360 die casting alloy, 535, a sand casting alloy usually, and a 713 alloy, so aluminum zinc magnesium alloy. And we can see they are all rated according to hot tearing, pressure tightness, fluidity, shrink, corrosion resistance, machinability, and weldability. So we can actually see in those tables that depending on what is really important for us, we might choose a certain alloy family, certain alloy type, and then we can maybe tune it. But then some of them might only be castable really in, let's say, die casting or a sand or permanent mold, or some of them really just in sand casting. And then if we look at comparative mechanical properties that are achievable with those alloys, well, we always have to start with the baseline, and that in the foundry world is A356. And A356 T6 is kind of the workhorse of the general foundry industry. I know if you're a die caster, then it is A380. But that's a different animal. So let's get started with A356. Typically, you look at 30 KSI yield, 40 KSI tensile, and somewhere, let's say, between 5 and 10% elongation. So let's say this is the baseline, and you can see that as soon as I go up in temperature, already at 150 degrees, the maxillocyte hardening loses its effect, and we're getting pretty much very soft, almost chewing gum style in the alloy. If we don't want to go through heat treatment, we want very good surface finish, maybe even anodizable part, and still very good mechanical properties, well, the 535 in F-temper, so S-cast, is an excellent solution. It's only 20 KSI yield, but equally 40 KSI tensile and 15% elongation. And that is S-cast, or here, 13, very high elongation. If I want to have really high strength, well, then we said that before, the 200 series aluminum copper alloys are the right choice. In T4, they give us very good elongation at the same time, and if we want to maximize strength, we might want to give them a T7. T7, because that avoids stress, corrosion, cracking that we would get in a T6. We cannot do a T6 with these alloys, very important to notice. But here we're talking about yield strength of 50 KSI, tensile here is 63, and still above 10% elongation. Copper also stays much stronger, much beyond the 150 degrees Celsius. Copper has a very good strengthening effect up to about 250 C. So we see here that even at these 175 C, we still have a very decent strength in the castings. If I need more strength at higher temperature, then I have to give it even a little more, and that in the 242 would be aluminum, copper, and nickel. This will really bring my elongation down. You can see it's only 1%, but it stays very strong even at higher temperatures. So now we have seen how many different packages of casting properties I can achieve, but very important, very rarely will I find just one set of properties all over a casting, especially if I have a big casting. So castings will get very different properties depending on the wall thickness, where it is close to the gating, close to the overflows and things like that. So it really depends on the microstructure, and therefore it's a local phenomenon, not just a general phenomenon all over the casting. So local solidification rate, interaction with gas and dirt, porosity in a certain area will really determine my properties. And then I should always calculate there will be a certain mean, a certain average property, and then I will have a certain spread. And very often designers will say, yeah, I will take the average properties and subtract, let's say 3 sigma, for example, and that's what I'm designing for. Others will just specify a minimum, and I need these minimum properties everywhere in the casting. Or some people will say, okay, well, I defined really these are minimums here, and then I have other areas where I have lower minimums, for example. So really the design properties must take both of these into account. And the other thing is the casting often have time-based component in here, so they might age over time, and they might see slow gradual chemistry changes and might even see seasonal changes. So that's why some people would want a T7 heat treatment, because that will stabilize the properties, for example. And the first economic law of castings is absolute perfection. The perfect casting will cost an infinite amount of money. So very important, define the casting that is feasible and define the properties that you really need, where you need them, and that will give you the most economical casting. So now let's start with alloys for high pressure die casting. It's the biggest consumer of foundry alloys, and it's the most common casting process, especially in North America. And I said it before, the most common alloy is A380, and that is made 100% from scrap. So usually what we call twitch. So when they shred a car, when they have taken off wheels and heat exchangers and everything you can take off, and it went through a sorting process and pretty much everything that you could recycle otherwise, and the ferrous scrap is taken out and it goes through a shredder, and then what you melt down, that is pretty much 380. I sometimes call it the garbage alloy, and I know some die casters don't like it when I say that, but for me the analogy is when I go to a recycling station and I have different bins for glass and for paper and for a can and all these things. Well, if I can't find another recycling bin that I could usefully recycle it into, well, then I throw it into the garbage. And that's exactly what A380 is. If I have aluminum, but I can't recycle it into anything else, I can always recycle it into A380. And why is that used in die casting? Well, actually it's quite ideal because it has a high iron content, usually up to 1.3%, which really prevents what I mentioned before, this die soldering. And due to the high injection speed of the metal into the die, I get this phenomenon, and with the high iron I can prevent it. But at the same time, if my iron gets too high, and even when you have A380, you should check your chemistry from time to time. I have seen A380 castings and they were not A380 anymore. They were actually much higher. They even had 3 or more % iron. And then you can get things like this, where the iron needles are actually platelets in a 3D space. They are so connected that they would just lead one crack all the way through the casting. That's very bad for ductility, and then the turbulent filling will cause a lot of porosity, especially in thicker walls anyway. A lot of people say die castings are basically two sound skins separated by Swiss cheese. And, well, it's kind of true if you look at this here. So that would be a typical thicker wall die casting, and it will have low elongation, both because of the porosity and the high iron level. But there's not just A380, there are actually a lot of different die casting alloys. The most common ones we see here, and that would be A360, 383, 384, B390, so very high silicon alloy, a 413, so almost eutectic die casting alloys, the C443, and then the 518, the 500 series die casting alloy. Now we can see all of them have one thing in common. They all have a very high iron level, and therefore if we look at their properties, which are really not that bad if you look at strength, so strength is pretty good, but all of them in F temper, because usually because of the porosity you cannot heat treat them. If you heat treat, the alloy will get soft and the bubbles will start expanding, and that's what gives us this phenomenon called blisters. And all of them have therefore very low elongation, and These are numbers from NATCA. I would say that normally in an A380, you will not see necessarily 3.5% elongation. You might see 1 or 1.5, maybe 2%. So these properties, pretty lucky if you see them. So now that's why we have actually what we call structural die casting or high vacuum die casting. And high vacuum die casting, well, it evacuates the die, the cavity, before we inject the metal. So I avoid this counter pressure, and I also avoid that I could entrap the air when I inject the metal at high speeds. But really, it's not just the evacuation, not just the vacuum that does everything. A lot of people think, oh, I just go to any die caster and I get them to buy a vacuum machine and then put it on the die, and then I get 15% elongation and all these wonderful things from structural die casting. No, I don't. If I want to go into really structural die casting, I have to do everything right. I need special alloys. I need special melt treatment and transfer practices. I need special gating, special lubricants in their application, all of these things. I need a much more holistic approach to the die casting process. And then I will need quality gates after every process step. So I'm getting into much more something like you would typically see in a structural low pressure die casting facility. So I need a spectrometer, I need maybe K-mol test, I need hydrogen measurement and density test, and I will do X-ray. Maybe I do weldability checks and crack inspection, and then I can now heat treat the parts, and then I do tensile testing and all these things. So I will have quality gates after every process step. My porosity and my defects are now really minimized. I can heat treat and weld it, and I can get very good properties. Also in terms of fatigue and crash, because the skin effect is still there, and now I don't have Swiss cheese between my very sound skins. Alloys for high vacuum or structural die casting have a few things in common. And the first thing is they are quite low in iron for die casting alloy. So you will often see limits on the iron of 0.15 or 0.2, 0.25 maximum. And they use manganese to beat die soldering, and even some strontium. The impurity levels are low, basically like primary alloys, and they require really clean scrap or even some primary alloy addition to make them. And the most common ones are the aluminum plus, let's say, anywhere between 8 and 11% silicon and a little bit of magnesium to strengthen them. You very often see brand name alloys, but you don't have to use the brand name. Most of them are registered with the Aluminum Association. So you have the Silifon 36, which is the 365 alloy, or the Oral 2, which is the A365, or you have the Oral 5S, which is the 374 alloy. And you have a lot of different trade names and Aluminum Association numbers, but we also see, also quite rarely in North America, but to some extent, aluminum magnesium silicon alloy. The most common one there is the Maximal 59, or even some aluminum iron magnesium, so iron as alternative eutectic, aluminum zinc magnesium, and aluminum magnesium binary alloys. But as I said, all of those are pretty rare. If you're interested in this, NATCA has a very nice standards book for structural die casting, and section 3 deals with the different alloys. Here are a few tables from this standard, so you can see the composition. It shows the iron pretty low, usually only some are 0.15 max, but most of them are more like 0.2, 0.25 max. Then the manganese addition, and as I said before, this is to compensate for the low iron, but typically between, we can see here in the Mercalloy, 0.25, and most others 0.35 or 0.40, and up to 0.8 manganese. Also low impurities, we see here copper and zinc, very often only 0.03 or 0.05. And then with this, we can achieve very good mechanical properties. So we see here the properties is published as cast, so in F temper. Some of them have very high ductility. For example, Castasteel 37, which has no magnesium, or Maximal 59, which is an aluminum silicon magnesium alloy, high magnesium alloy with low silicon. And those ones, for example, are not heat treated, so you get these properties really as cast. And others are usually heat treated, And we can see here now in the table the different heat treatments, very often a T7 or a T6 heat treatment. And we can see the property packages that we can get there. So still decent strength and very high elongation, often well above the 10%, often even above 15% elongation. In these alloys, usually we tune the silicon content to good castability and then the magnesium content. And with the magnesium, we tailor strength and ductility. So if we have lower magnesium, we will get higher ductility, but lower strength. With higher magnesium, we get lower ductility and higher strength. With that, we can see here, we can clearly tailor it. And after that, it's, for example, with a T5, I do artificial aging, and from the AMCAST status, I then increase my strength at the cost of ductility. Very similarly, we see this here with the oral alloys, although it's registered both under A365. Oral 2 here is the lower magnesium, usually 0.3% magnesium, and oral 2 is the low magnesium, and oral 3 is the high magnesium. So it can be confusing. Oral 2 is 0.3 magnesium, and oral 3 is 0.5 magnesium. And we can see that on the right here with the properties very easily. AMCAST, right away you see that strength goes up with higher magnesium and ductility goes slightly down, and that's of course even more pronounced when we go with heat treatments. Here the oral 3 properties are all stronger and with lower ductility. So with this, let's have a look at the alloys for all the other casting processes. Anything but high pressure die casting. So now we're dealing with the slower solidification rate, and that means larger SDAS, SDAS. That means secondary dendrite arm spacing. So when we solidify metal, usually we are seeing these dendrites, and that comes from the Greek word for tree. It looks like a tree the way it solidifies. So the larger SDAS, the lower the elongation. So the slower the solidification, the lower the elongation. And that makes it very clear if I look into a casting, for example, as soon as I have a thick section, that means I will get slower solidification, and that's typically where I will see lower elongation than in a thin-walled rib, for example. You can see this very nicely here in the picture. So that's what we just saw, slower solidification, so which really means in sand casting, or if I have sand cores in permanent mold, I will get larger SDAS, I will get lower elongation. And if I want to compensate for that, because, well, I want to make sand castings, I know I will have a slow solidification rate, but I really need to have very good properties. So I want to counter that with the alloy, and I can do this by lowering the iron content. This was a study from Jeffrey Sigworth, and that's a while ago, but it's still very valid. And you can see here that, well, depending on the heat treatment, obviously I can get different property packages there, and I can trade in elongation for strength, but with a certain iron level, I will stay in one curve. So I can see here that if I want to move this curve outward, I want to gain elongation and or strength, I need to lower my iron content. And that's why some aerospace foundries, they will actually use very high purity alloys. And with high purity, I can get exceptional properties, even with a slower solidification. So that makes it very clear that if I'm casting into steel molds, then this is much less forgiving in terms of shrinkage. So I will get more hot tear if I use hot tear sensitive alloys. And that's why I mentioned this before, like an A206 or a 242 alloy, even a 535, they are much easier to cast in sand molds because they are not so rigid. They will not hold it so hard in place. They will give in a little bit. Now, 300 series alloys clearly presents the majority of foundry alloys, and they can be used really for most applications. The 200 series alloys, as I said, is really the alloy family for high strength applications. The 500 series alloys are used for surface finish. If I want anodizing, if I want high corrosion resistance, things like that, that's where I want to go to a 500 series alloy. And 700 series is now aluminum zinc, sometimes with magnesium. That is ideal for very large sand castings or also anodized and for brazed components. So let's get started with 300 series alloys. So why would we use a 300 series alloy? Well, first of all, it has very favorable characteristics, like it's largely immune to hot tearing, which can be a huge issue if I want to go into steel molds. It's very, very castable. It's ideal to cast. That's why A356 is the workhorse of the permanent mold foundry industry. And it's relatively inexpensive. It's really a commodity. A lot of those alloys, you can get them from many suppliers at a very cheap price. They should be considered then if the part in question is very complex, if it's not possible to achieve steep temperature gradients and very directional solidification, and it's impossible to avoid mechanical restraint during the solidification. Or simply if there is no reason to specify one of the other families, because I don't need to have the capability of, let's say, anodizing the part, or it doesn't need to be brazeable and doesn't need to be super corrosion resistant. I just want it to be easier to cast. So that is why this is the industry default alloy series. So now if we look at the schematic aluminum silicon phase diagram very quickly, we see at the very left it would be no silicon at all, and the more we go to the right, the more silicon we get. Typically, we can see that in the 5 to 8% silicon alloy, we find most sand and permanent mold alloys. So A356, 355, 319, 320, all of them are in here. They're very easily castable, very forgiving, very good properties, depending on whether I want them at a room temperature or slightly elevated temperatures. And then between 8 and 10% silicon is where I see most of the die casting alloys. So 360, 380, 383, they're here. If I go higher in silicon, that's where I will find some more die casting alloys, but I find the piston alloys. So typically 10 to 13% silicon. And if I want to go much higher up, so then I become hyper eutectic, that's where I see the 390 alloy is the most typical high wear resistant alloy. So as soon as I need to be wear resistant, then I'm using the 390 type alloy. Other elements such as copper and magnesium are added to add strength that I can get heat treatment responses, and the binary aluminum silicon alloys, they would be usually 8 to 13%, so nearly eutectic. 413 is the most common one as a eutectic alloy. That's ideal for very thin-walled, intricate castings, but it's not very suitable for thick walls. You will get solidification shrinkage and hot spots unless you really have directional solidification, because the whole thing, it just goes from liquid to solid in one point. You don't have this large, what we call a freezing range. And here we can see a few example micrographs from different regions of this aluminum silicon diagram. And you can see very easily, it looks very, very different. So on the left, on the top, we have a nice A356. So the white or light gray, if you want, that's the alpha aluminum. That's the aluminum that solidifies first. And then we can see this structure between, that's what we call the eutectic liquid that solidifies after. And we can see if this is fine-grained and not lamellar and has a structure like that, that means it is actually nicely modified. So this will give us a very nice property package with high elongation. If we look to the right, A380 die casting, we can see there are big intermetallics. We can see there are iron needles. There are a lot of things that will definitely block if we pull this alloy, and therefore that's where cracks will easily initiate, and that's why we will not get much of an elongation out of this alloy. On the left bottom we see a piston alloy, and we certainly don't want high elongation in pistons. There we want high temperature stability, so very important. And then to the right is the Mercosil 390 type alloy, 392 in this case, and now we can see actually the slightly dark gray, that is the silicon that now solidified first. So remember, we are hyper eutectic, and the silicon will give us this very good abrasion resistance, the very high strength, and making it ideal for anything where abrasion is the main criteria. Now let's look at the subgroups or subcategories in the aluminum silicon copper series alloys. We have the low copper, so there it's just a trace element in 356 or in a 360 die casting alloy. And then we have the intermediate copper alloys, and there you might be somewhere around 1%. So it's just added a little bit to give you a little bit higher temperature stability at a slightly elevated temperature. So that would be like a 354 or 355 alloy. And then we have the high copper alloys, and they are typically 3% and up. And that would be either for sand and permanent mold, the 319 or 320, and typical applications here would be like engine blocks and cylinder heads, things like that, where I do not want much of an elongation, but it's exposed to a lot of heat in service. Or, of course, the die casting alloys 380 and 383. Let's talk about the workhorse of our foundry industry, the 356 or 357 type alloys. Well, the advantages are pretty clear. We have a relatively high strength and ductility. It's ideal for structural components. We have largely immune to hot tearing and cracking alloys. We have the largest database on mechanical performance, mechanical properties of any casting alloy family. Pretty high thermal conductivity in comparison to, let's say, a 319 or a 380. Good corrosion resistance and pretty good fatigue properties. Now, the disadvantages, of course, is it must be heat treated to achieve really high strength and hardness, which adds cost. And the cost is higher if we're looking at the primary A356 than, let's say, a secondary 319 or let alone a 380 alloy. The major uses are of wheels. For A356, that's the biggest use in North America. Higher purity versions go into aerospace castings, all kinds of structural parts, automotive suspension components, subframes, cross members. It's frequently basically used as the general purpose casting alloys. Within the family, we distinguish between different types, and we learned in another webinar that the first to register an alloy will get a 3-digit number, and that in this case is 356. The 0.0 is the casting specification, 0.1 the ingot, and 0.2 the higher purity ingot version. So we see a 356.2 would be a 0.13 to a 0.25 iron, and then the A356 really starts already in the casting with 0.20, and then the 0.1 is 0.15 and 0.2 is 0.12 iron. All of them same silicon level. It's always about 7%, 6.5 to 7.5, and magnesium in the range of 0.3 to 0.45. Oddities in this family is really the F356, which is a low magnesium version. So it's usually about 0.2 only, which trades strength for ductility. And then the C356 is a very low iron, below 0.07 in the casting, 0.04 in the ingot. The related alloy is the 357 family, which just adds more magnesium. The 355, which adds a little bit of copper, and then the 360 variant, which is a die casting alloy. We have seen this before, but let's have another look at the impact of iron on mechanical properties. In this case, a 357 type alloy. So at a given freezing rate, we can increase the yield strength, as we can see here, and we know also the elongation by reducing the iron content. So we're coming usually from a primary version of, let's say, a 0.10 or a 0.11, and then we reduce the iron content, and we can see going down to 0.08 already increases it quite a lot. But if I go beyond that and go down to a 0.06 or a 0.05, I'm gaining a real lot. I can gain almost 10% by going from a typical 0.12 down to a 0.03 iron level. And that is a very useful thing to know. In 357 alloys, the A357 contains beryllium. Beryllium is used on the one hand to reduce drossing and oxidation in aluminum alloys if we have a higher magnesium content like we do in a 357 type alloy where we have 0.5, 0.6. But it's considered a health hazard. It can cause berylosis. But it is also proven to impact the iron phase morphology in these type of alloys. So you change the iron phase, and that beneficially impacts ductility, and we can see here the yield strength as well. So that alters the balance between the mag available in solution and that tied up in the iron phase, and hence the yield strength plot for non-beryllium containing alloys can be corrected. with beryllium. Therefore, newer variants of the 357 type alloys are all very low iron type alloys, and they typically don't exceed 0.07%. So let's have a look at these new 357 variants. They are all spec'd with 0.04 to 0.07% beryllium, and previous non-beryllium variants that weren't registered with the Aluminum Association were usually already produced with below 0.06% iron. And if we look at those new variants, they're registered under E and F 357. The F357 is the by far more common alloy. All of them, as I said before, are 7% silicon. The iron maximum is at 0.07 here. The F variant has a limit on copper and zinc and has a wider range on magnesium and titanium. The rest is pretty much the same. So if we look at properties achievable with this F357 and T5 with just different magnesium contents, again, to show the impact of magnesium. So we can see here very clearly on the left-hand side, we start with 0.4% magnesium, and depending on the aging, we can see here the aging will trade in some of the ductility for higher strengths. Elongation in green, it's going down, and the blue and red are the strengths, yield and tensile strength. And we can very easily see just by adding some more magnesium, going to 0.55 and then going to 0.7, we see a big increase, and very nice increase also in heat treatment response. So we're getting stronger and stronger and losing ductility for that. So now let's go into the role of each element very quickly. Again, copper, it's a strengthening element. It's relevant at elevated temperatures. So if you watched our webinar on alloys, we went into more depth regarding this. It also reduces shrinkage, ductility, and corrosion resistance. That's why it usually is minimized in alloys that are used in applications that go into, let's say, marine or any corrosion-resistant application. And copper also needs to be limited in some structural castings to guarantee good weldability. And there's generally limited to just 0.3 or 0.35 max, so not as low as we see sometimes for corrosion resistance. There you might see an 0.03 max, for example. So if we add copper to the 300 series aluminum silicon alloys, we get to alloys like the 319, very common alloy for cylinder heads, for example. It has about 6% silicon and 3 to 4% copper, and other than that, it doesn't really have much else. It is usually a secondary alloy and therefore has relatively high iron content. Similar variant would be the 320 with 5 to 8% silicon and 2 to 4% copper, but this one we also have magnesium in the typical 0.1 to 0.6% range, and we also have more manganese in there. So as I said, these are secondary alloys, higher iron content, so an iron phase correction is very important, and if we are at the typical above 0.5% iron, we usually say we want to add about half of the iron content as manganese. So this will modify the iron phase and create the Chinese script. Related alloys are, of course, the workhorse of the die casting industry, the 380 type alloys, A380, and then piston alloys like the 330 series with elevated silicon and nickel. So what does the copper really do in high temperature alloys? So as I mentioned before, the typical aluminum silicon magnesium, the max silicide hardening, is losing its strength very quickly, and especially after about 150 degrees Celsius, we can see a pretty dramatic drop there. So that's what we see in the red arrow here. So very quickly, I'm going from 150 and I'm at 200 megapascal strength, and at 200 degrees Celsius, I'm down to just about 50. So I have lost 75% of my strength in just 50 degrees Celsius. So that is a lot better when I add copper. First of all, copper is pretty stable now until about 250 degrees Celsius. And even after that, we can see the drop within 50 degrees is not 75%. It's really just a slight drop. So that's very important. This is why we are adding copper. And at the same time here, we can see elongation goes up very, very quickly. It goes up before already until 150, but after 150 degrees Celsius in a 356 type alloy, my elongation goes up incredibly. So at 300 degrees, I have over 60% elongation. That means it's really already a chewing gum. And that is not the case in the 319 alloy. So the 319 keeps its strength and doesn't gain that much ductility. So here we see yield stresses for common cylinder head alloys. So cylinder heads are of course exposed to pretty high heat, a lot of cycles going from hot to cold, and a lot of stresses in there, and especially the intervalve bridge is really exposed to a lot of those stresses, and after a while we see it will just fatigue and will start to creep. If we look at the different alloys that we have here, we see in white the C355, and of course in yellow we saw that before, that is our A356, and we see the A356 drops very quickly in yield strength here, and it gains very quickly in elongation. We saw that before. If we look at alternative alloys here, that would be the C355. We stay pretty stable, at least until the 150, because we have a bit of copper in there, but then we drop pretty quickly. If we look at this one, it would be the 242 alloy. So in that case, we're staying stronger for a longer period of time. We see until 250 at least, well beyond the 356 or 355 alloys. And if we want to go well above that, then we would have to go to the 242 or even the Rolls-Royce 350 alloy. So that would be the cobalt-containing alloy. Those were the very traditional alloys, but we found, of course, that we can add a couple of very simple additions to existing alloy and make them a lot more temperature resistant, stronger at higher temperature, and creep resistant if they are exposed to high cycle fatigue. So if we look at three typical cylinder head alloys, so the first one is an A356 in T6, and the second one is a kind of 319 primary and then a 319 secondary alloy. So creep resistance is very low in A356 because we have no copper in there. We have seen it get very weak very quickly. That is pretty good in the primary 319 alloy. If I have just an F-temper secondary, it's more medium. Ductility, on the other hand, is the opposite. That's very good in A356, but only medium in the primary 319 and pretty low then in the secondary 319. So these would be the typical properties that we can see in the primary A356. At room temperature, 200, almost 300 megapascal, and 15% elongation. So that changes very quickly. At 250 degrees Celsius, we have seen that before, I'm at 57, 69 strength and 29% elongation. At 300 degrees Celsius, I have complete chewing gum. If I go to the secondary 319 type alloy, 0.7 iron, this is AMCAST, so I'm not that strong, and I have low elongation as cast, but I am by far not losing that much if I go to 250 degrees. But if I go to 300 degrees Celsius, the aluminum copper strengthening mechanism weakens up, and even there I can now see 12% elongation, and my creep resistance has gone up a bit, but it's not where I would like to have it. If I use the primary version of the 319, so the last line here, I can see in a T7, I'm starting off much stronger, but at 250, I lost a lot of that strength and I gained a lot of ductility. And at 300 degrees, I'm again down to pretty much chewing gum, but my creep resistance is basically the same as in the secondary version. So we have to ask ourselves, isn't there anything else that we do to make this a lot better? And that's where nanoparticles, dispersoid hardening elements are coming in. And we have found vanadium and zirconium, for example. They have chemical properties very similar to titanium, and at very small concentrations, they can really do great things. So we just need to add a bit more than 0.1%, and we form these dispersoids. And we can see them in the microstructure. They're really like a metal matrix composite then, just in the nanoscale. Molybdenum is a similar thing. It's also virtually insoluble in aluminum and has very limited solubility in liquid aluminum, forms the intermetallic compounds with aluminum, and that is solidification. So it's equally a dispersoid forming, strengthening agent. Also, another one would be the scandium, and that would have a lot of other very nice side effects. So it inhibits recrystallization, it's strengthening, it's a grain refiner at the same time, and a modifier. The only downside is it's ridiculously expensive. So you really want to stay away from that one unless money is really not an object. If we look at what we've done in the high temperature cylinder head alloys, the improvements upon the A356 T7, because that is the typical starting point, is that first of all, let's add 0.5% copper. So we have seen that adding a little bit of copper helps already up to 250 degrees Celsius, and we can see this here. If we start, we have seen these numbers before. At 250, I'm already very soft. At 300, I'm complete chewing gum. If I add the 0.5 copper, well, no surprise, I'm getting quite a bit of a strength boost at 250. I do not have any effect beyond 250. At 300 degrees, I'm just as bad as if I didn't have copper, because I said it before, copper loses its strengthening effect after 250 degrees Celsius. So this is really where we kick in with our dispersoid hardening elements. And in this case, we use zirconium, and the manganese is in there because it actually enhances the effect of zirconium. So we still have the 0.5 copper in there, still the A356 as the base matrix alloy. So our room temperature properties, no surprise, are pretty much the same as we had before with regular A356 or the one with the 0.5 copper in there. And the 250 degrees Celsius properties are also quite similar to just the regular copper containing alloy, because usually at room and lower temperatures, these dispersoid hardening elements don't do that much, but they really kick in when it gets hotter. So at 300 degrees Celsius, we saw that even just a tiny little addition of 0.14 of zirconium and about the same amount of manganese gives me a 10% boost in terms of high temperature strength. So now if we have a look at the effect of copper, and we can see it here at 20 degrees, the effect is very big. We can see here on the left, we start with just below 2.5% and go over 4%. So we can see there's a linear increase in yield and tensile strength if I add more copper. That is still visible if I go to 250 degrees Celsius, these pink lines, although they're much flatter. And it gets pretty flat as soon as I go to 300 degrees Celsius. So no surprise there. If we look at the summary here, so we started off with A356 and added 0.5 copper to it, and then a little bit of zirconium. And with that, we had first an increase in 250 degrees Celsius strength, and then with the zirconium also at 300 degrees Celsius strength. If we want to go higher than that and want to really make it much stronger, we found that if we add 3.5% copper, so we are in the middle of that range that we just looked at, and we can see that now we basically double the 250 degrees Celsius strength and still get pretty decent elongation. And now we really boost the 300 degrees strength from just 40 megapascal to 66 or 63, and the 44 tensile to 75 to 77 megapascal. Still getting pretty decent elongation. If I actually wanted to go higher than that, I would have to go to a 200 series alloy, and then it would be a lot higher, but I would not see the same elongation at higher temperatures. Now, what's really important in these cylinder head alloys is, of course, the creep. Creep resistance, ternary creep resistance at 300 degrees Celsius in that intervalve bridge. And here we see actually the comparison between, in blue, the top lines, they are just the regular 0.5% copper addition to an A356. And as soon as I add the zirconium to it, I'm getting to these green lines, and we see that the strain is going down quite a bit. So I can see that the real effect of the zirconium addition is not just that I make them stronger at higher temperatures. I'm really making them stronger and more resistant to this ternary creep that's happening in such an application. If we look at more of these alloys that have been developed in the meantime, people have played around with the silicon content. Here 9% silicon with 2% copper or 3.5% copper, and we can see the mechanical properties. And then, of course, the difference between fine and more coarse microstructure and the impact of it. But we can see that the trend is always pretty much the same, and the tricks have remained the same. We're playing with copper addition, and we are playing with the addition of other elements. So here that was the room temperature properties of the three alloys, and then we can see at 250 degrees again we see a big difference with the addition of copper, and then here at 300 degrees Celsius again. And it's really depending more on the zirconium that was added to the 9% silicon alloy, again in combination with about the same amount of manganese. And we see here again the creep. So the regular A356 with the small copper addition, the 0.5% copper, we see it creeps very, very quickly and quite dramatically. So if we look at the aluminum silicon 9% and with the 2% copper, and here we can see again that was the 0.12 zirconium with the 0.13 manganese, the blue line much lower, and even lower if I add the 3.5% copper and about the same amount of zirconium and manganese. So now we've talked a lot about copper addition, so let's talk about the 200 series alloys. And why would you use a 200 series alloy? Well, it's the strongest of all aluminum casting alloys. It was actually the first element historically that was added to aluminum to make it an alloy and to make it strong. And if you look back at early World War I or II fighter planes, the alloys, the aluminum alloys used there were all aluminum copper. Actually, a lot of structures back then used this, and one name that you might still find out in the industry is duralumin or duraluminium, and so from strong. That was the first alloy called aluminum copper alloys. It exhibits a high temperature strength. We have seen up to 250 degrees Celsius. Lack of significant intermetallic content leaves them pretty ductile even when they're tempered to high strength. And you might remember, do not treat them to T6. Usually it's a T4 if you want strength, or T7 if you want them long-term stable with high strength, and you can live with a little bit lower ductility. They should be considered when strength and fracture toughness levels are unobtainable with any more user-friendly alloy, and the castings are compatible with sand casting, or the part geometry is really simple. So you could actually do it in permanent mold and make sure the foundry is actually experienced in permanent mold casting of hot, short alloys like this. And I'm pulling out one example that I think we presented back in 2007, so a long time ago, but that was, as you can see, a knuckle, and it was an A206. It was in T4 temper, so to give a very high ductility, but still very good strength, and it was quite a challenge. So it was a direct replacement for a cast iron, because the A2 has very similar properties as cast iron. High volume production, you can see it's package constrained, and we had 20% initial hot tear scrap in there, and you can see in the circle in that one boss. So one trick was hot ejection that was used to minimize the hot tears, but that led to some bending, and actually in service there were never any issues. So the small boss would sometimes tear off, but that just shows that part design is really critical. If we look at the 206 alloys, that would be the 206 in B206 this time in a T4 temper. We can see again, we can play with the copper content. You see here plotted strength and elongation over the range of 4 to 5%. And we see this goes up pretty quickly, and we can reach levels that are pretty impressive. Again, now with lower iron, I can get better properties. And in this case, silicon is also an impurity. So if I lower both silicon and iron, I will get the highest curves here. So I can reach levels of 280, 290 megapascal yield, well over 400 tensile, and still get a very good elongation, over 15% elongation. Even in slow solidification processes with large grains, I would still get more than 7% elongation, and it's less sensitive to impurities in the T4 than in the T7. In the T7, if we look at that, we get the very high strength. So now I'm both with yield and tensile well above the 400 megapascal. Now my elongation is clearly down. It can be as low as just 3.5 to 4%, but I can still create a variant that gives me 6, 7, 8% or even 10% elongation. If I want to do that, I need a very low impurity, very high purity alloy, and ideally pretty rapid solidification, so either in a permanent mold or with chill blocks. Now let's talk about magnesium quickly. And magnesium in aluminum magnesium binary alloys, so the 500 series, they really have excellent mechanical properties as cast. They offer pretty high ductility there. They have excellent physical properties, finishing characteristics. It can easily polish and anodize. That's really the choice that you would normally make when you have that requirement. I need very nice surface finish. I need to anodize the part. And they machine very good. They are extremely corrosion resistant, so any kind of marine application, if you don't know what to take, that would usually lend itself to a 500 series alloy. But mind, they are more difficult to cast. They have relatively poor fluidity and high solidification shrinkage. Special handling is required to control the selective oxidation of the magnesium phase in liquid conditions, so therefore very often you see a very small beryllium addition. So be careful when you are machining these alloys. Make sure that all the dust is captured. Do not polish them somewhere just in an open shop or so. Favorable characteristics and unique to these aluminum magnesium, the 500 series alloys, are strength and ductility, serviceable for many applications, and all in the F-temper, so no costs for heat treatment, then also no distortion coming from heat treatment and the quenching. Excellent corrosion resistance, I said that. Easy machining, very good polishing, it can be anodized, and they should therefore be considered for marine applications and any surface appearance critical outdoor exposure parts. We see nowadays more and more parts that get special anodized, antimicrobial anodizing and things like that. They are ideally compatible with sand casting, or if the part geometry again is simple enough, then you can do permanent mold, or in some cases even die casting. So now let's have a look at zinc. And zinc would be, of course, the 700 series. Zinc has a very wide solid solubility range in aluminum. It can provide solution strengthening effect at higher concentration, but be aware that excessive amounts can cause cracking tendency. It can improve machinability, and in small amounts of up to, let's say, 0.2 or 0.3 in aluminum silicon magnesium alloys, zinc has very little effect. In most of the alloys, if you go a little higher, it can use as a strengthening element in combination with special heat treatments. But I have heard it can be problematic for bonding the castings later on. These special heat treatments, they have to be really tailored, and very often you see not just the typical 2-stage solution heat treatment and then aging. You might see actually 3 or 4 stage, so you have different temperatures for solution heat treatment and different aging temperatures, and so it takes quite a bit of skill and playing around with it to find the optimum heat treatment for this. Now, in combination with copper and or magnesium, it can result in very attractive heat treatable and natural aging compositions. But mind, again, not just iron, silicon as well is now an impurity in these alloys. It is also said to enhance surface corrosion, so sometimes zinc is added to other alloys to protect them from filiform or any deeper kind of corrosion. What are the criteria for selecting 700 series alloys then? Well, the favorable conditions characteristics are moderate to high strength as naturally aged, or just a T5 alloy. That's actually the one that can be brazed, and it's really the only one that on the alloy family that can easily be brazed. We do not see thermal growth, so we have very high dimensional accuracy, and therefore it's ideal for a large casting requiring high strength, and they are too thick to heat treat if the parts have to be brazed or anodized or both. Tolerances are critical. It's used, for instance, for the molds for blow molding plastic. And if you really need to avoid heat treatment, the natural aging usually takes place within a time frame of 3 to 4 weeks, and then you're pretty stable. Mind that corrosion should better not be an issue, especially stress corrosion. They have a tendency for stress corrosion cracking as well, especially if you do it in a T6 temper. The castings are best compatible with sand casting or again, if you have very simple geometry, it can be done in permanent mold or even in die casting. So here we have a nice example. It's getting pretty old as well, but it's still nice to look at. That's the Ford Pinto back then, the intake manifold, and that was actually, you can see it on the right, a brazed assembly of raw tubes and a 712 alloy casting. Now, I said it can also be die cast, and it's not very common to use this, although I've heard of people developing more 700, or sometimes they call it 7000 series alloys because it just sounds more aerospace type. In any case, aluminum, zinc, magnesium alloys, we can see here the properties of the 705 and 707, and those properties are actually reached with just natural aging, and we can see here that the strength develops very quickly after just a couple of weeks. We see after 3 weeks we're already at a very high level, and then we see a small change after going to 6 months and 1 year, but it gets pretty flat after that. And the properties are pretty good. If we look at elongation, the 707 can reach 15% elongation and give you 140 and 250 yield and tensile strength. So very nice packages, achievable and without any real heat treatment. So with that, we come to the conclusions, and really we have seen alloy selection is first of all driven by the specific casting requirement and the casting process that you've chosen for your specific casting based on whether it's volume, wall thickness, tolerances, surface finish, and so on. Certain casting processes require certain foundry alloys, and some can just not cast certain alloys. They would just stick in the die, for example, or they would shrink too much and they would just crack before you even open the die. Certain alloys can only be cast in specific processes and not in others. And aluminum foundry alloys can really be tailored to many different requirements, many different properties, just through the right composition. So if you look through the books and through standards and whatever you can find and you don't find exactly what you're looking for, well, maybe just talk to us and let's have a look what you're exactly looking for, and I'm sure we can find a way to tailor an alloy to meet your requirements. Now, the casting process, the solidification rate, and the heat treatment, they also play a very big role in the properties of the final casting. So therefore, they also need to be taken into account, and we would do that as well and find the right solution for you. With this, we're coming to the end of this webinar. Thanks for staying with us until now. If you have any questions, you can see my email address and Jay Armstrong's email address is here. Let us know any questions, anything you would like to have in addition, anything you would like to have on top of what you've seen. Send us an email. We'd be happy to get in touch with you. Thanks a lot. See you soon.